So sets and set operations. So we're going to define a set. So intuitively, a set is just a collection of objects. An object that belongs to the collection is called an element or a member of that set. The universe is all objects that are allowed to be in consideration as elements of the sets. There are only two choices for objects of the universe. It's either in the set or it's not in the set. There's no in between. So this is called the law of excluded middle. You're either in the set or you're not in the set. There's no halfway in between. You can't be kind of in a set or on the border or anything like that. It's a binary choice. So there are multiple ways that we can define a set. One of them is to just describe it in words. So for instance, the set of the first 3 presidents of the United States. That's a perfectly well-defined set. We could also list the set, which is something we've done and in previous classes and a little bit here, as the set S is equal to George Washington, Thomas Jefferson, and John Adams. Right? That's just an enumeration of all of the elements of that set. The other one is set builder notation that we've seen in our algebra classes. So the set of all x's such that x is one of the first 3 presidents of the United States. All 3 of these represent the same set, which is the first 3 presidents of the United States. And we're talking about ways to talk about the objects in these different ways. So we will use all of these at different points, but oftentimes, if possible, it is nice to be able to just enumerate all of the things that are in the list. Sometimes that's not possible, and we'll have to settle for giving a rule for inclusion. And that can be for many different reasons, as we will see. So a couple of symbols that go along with set theory. And some symbols that we're going to need to know is when we've been talking about numbers in math class, we use equals and not equals. Well, oftentimes when we're talking about sets, we're more concerned about if something belongs to some set. So when we're talking about sets, we will use capital letters to represent sets themselves, and we will use lowercase letters to represent elements of a set. The symbol right here means that the element x is in the set S. So that is our abbreviation for in. We also have this one with the line through it, which means not in. So when we want to talk about our sets, remember, an element is either in a set or it is not in a set. So if it's in a set, we use our in symbol. If it's not in a set, we use our not in symbol. So example 1, if we have the set containing apple, banana, and kiwi, apple is in the set, but golf club is not in the set, right? That set has exactly 3 elements, apple, banana, and kiwi. So we would say apple is in the set, but golf club is not in the set. We say 2 sets are equal if they have the same elements. So 2 sets are going to be equal to each other when they have the same elements. So in example 2, the set S and the set T are equal. Set S was apple, banana, kiwi. Set T is kiwi, apple, banana. The reason that this is true is sets are unordered. So any ordering of the elements is possible and doesn't change the value of the set. So all we're saying is for 2 sets to be equal, they have to have exactly the same elements. The order that they are listed in inside the set is not important. So the set S and the set T are the same set, because they both contain 3 elements, and those 3 elements are apple, banana, and kiwi. Our next definition is the following, which is a subset. A set S is a subset of another set. That should be a capital T. If every element of S is also an element of T. So the symbol looks kind of like a less than, but it's rounded. So S is a subset of T. A set S is a proper subset of T if every element of S is also an element of T, but S is not equal to T. So every set is always a subset of itself, but we call it a proper subset if the set does not equal the set that it is being compared to. So, for example, once again, if we have apple, banana, kiwi is S, and T is kiwi, apple, banana, and R is apple, banana, S, R, and T are all subsets of S. R is a proper subset of both S and T, because R is completely contained in each of these sets. But we have the following, that R does not equal S and R does not equal T. So that means that R is a proper subset of S and R is a proper subset of T. So a memory aid that might be helpful for each of these is when we have subset, you'll notice it's got the little line on the bottom, like what we had with inequality symbols. So that's like or equal to. When we have a proper subset, you'll notice that it does not have the line underneath it, right? Which is like the difference between 4 is less than or equal to 4, but 4 is not less than 4, right? One of those allows the or equal to, the one with the line underneath. The one without the line underneath does not allow the or equal to. So the subset operation is actually very similar to this idea of inequality. We'll see that there are certain things where they behave in very similar ways. So proper subset, once again, is it is a subset, but it is not equal to the set in question.
For it to be equal, it has to be the identical names in each set.
Mm-hmm.
Doesn't matter
The order doesn't matter. They just have to be the same. So the last symbol we are going to need is the empty set symbol. So the empty set symbol looks like a 0 with a line through it. This is for the set that contains no elements. This is also why mathematicians never put crosses through their zeros, because that symbol means something else. So the empty set is the set that contains no elements. So in brace notation, we would write it like this, because it contains nothing in it. A type of set that is often used, and what we're going to be focusing on, is the set of all outcomes or possible outcomes of an activity or experiment. This set is also known as the sample space. So when we're talking about an event, the sample space or the set of outcomes is all the possibilities that could occur. So let's take a look at example 4. A quarter is flipped 1 time. So let's enumerate all of the possibilities. So what are the 2 possible outcomes of flipping a quarter? There's 2 sides. So we could have a head or we could have a tail. So that set contains 2 events. Oftentimes for coin flips, we'll just do H and T, right? Heads and tails. So if a quarter is flipped 1 time, the set of possible outcomes is heads and tails, right? Let's take a look at our next example. So in our next experiment, we have the following. A quarter and a dime are flipped once. What are the possible outcomes? Well, we're going to have to be a little bit careful when we do this, because now on the quarter, what are the possibilities? Heads or tails. And what are the possibilities on the dime? Heads or tails. But if I get a head on a quarter and a tail on a dime, is that going to be the same as a tail on a quarter and a head on the dime? No, because the 2 coins are different. We can tell them apart, right? Each coin has both a head and a tail, but the coins are not the same coin. So to help us visualize what's going on, let's make a table. And I'm going to put my quarter across the top and my dime down here. So my possibility for the quarters is once again, I can have a head or I can have a tail. And the same thing is true for the dime. I can have a head or I can have a tail. To help me distinguish between the 2 things, I'm going to change the color of my dime to red. So then up here, my first possibility would be a head on the quarter and a head on the dime. My second possibility would be a tail on the quarter and a head on the dime. My third possibility would occur here, which is a head on the quarter and a tail on the dime. And lastly, I could have a tail on the quarter and a tail on the dime. So then my set of possible outcomes would be the following. I could have a head. I could have a tail head. I could have a head and a tail. And I could have a tail and a tail. So then we've listed or enumerated all possible events. So how many outcomes are possible if I flip a quarter and a dime?
Mr. Peterson?
4, right? So there are 4 possible outcomes to that experiment, or the sample space has 4 things in it.
Professor Peterson?
All right. So now we have to be a little bit careful. So what if I have 2 identical quarters? So there is no way to tell them apart. All right. So now example 6 says 2 identical quarters are flipped. So unlike what was happening here, we cannot distinguish one coin from the other. So our possibilities are that we have 2 heads, we have 2 tails, or we have 1 head and 1 tail. And a tail and a head would be the same thing. So in this case, our probability space would only have 3 events instead of 4. So knowing if we can distinguish objects or if things are distinguishable is going to be important because it's going to change probabilities. Because if we can't distinguish objects, then this probability space would only have 3 things as opposed to 4. We have a couple more examples that we'll use to illustrate this idea. In fact, that is our next topic. Distinguishable versus indistinguishable. All right, so we want to build up this idea that we've just seen in those 2 different examples. So distinguishable versus indistinguishable. So we have 2 dice are rolled. Well, what is the sample space? Okay. Let's start by making a table once again, and then we'll try to break it down into distinguishable and indistinguishable. So if I have a die, what are my possible outcomes? Well, let's say we're using a standard 6-sided dice. So we can roll a 1, a 2, a 3, a 4, a 5, or a 6. So we could have 1, 2, 3, 4, 5, and 6. Same thing here. 1, 2, 3, 4, 5, 6. I'm going to space those out a little more. 1, 2, 3, 4, 5, 6. So that means here I'm going to have 1, 1, 1, 2, 1, 3, 1, 4, 1, 5, and 1, 6 are my possibilities. Next, I'm going to have 2, 1, 2, 2, 2, 3, 2, 4, 2, 5, and 2, 6. My next set of possibilities is 3, 1, 3, 2, 3, 3, 3, 4, 3, 5, and 3, 6. And we have 4, 1, 4, 2, 4, 3, 4, 4, 4, 5, 4, 6, 5, 1, 5, 2, 5, 3, 5, 4, 5, 5, and 5, 6. And then finally 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, and 6, 6. So on my first die, I could roll a 1 through 6, and on my second die, I could also roll a 1 through 6, right? Okay, so in this case, I see 36 are my dice. I have 36 things because 6 times 6 gives me 36 possible outcomes. In this scenario, are my dice distinguishable or indistinguishable?
Indistinguishable because it's the same dice, right?
Well, if I have 36 things listed, can I tell these dice apart? Am I counting this event right here, 1, 2, is it different than a 2, 1? No, right? So in this case, there are 36 when they're distinguishable. So this is the example of distinguishable. Because 1, 2 is not the same as 2, 1. If my dice were indistinguishable, what would have to be eliminated? It would be everything down here on this lower half, right? Because then all of this down here would match up with one of the things up there. So then with distinguishable, we had a total of 36 events. Here, if I eliminate all those, how many things am I going to have? 6 plus 5 plus 4 plus 3 plus 2 plus 1. So that's going to be 21, right? 11, 15, 18, 20, and 1. Perfect. So if we can't tell the dice apart, it's going to be indistinguishable. So our total, sorry, that's a little deceiving. I should shade these ones in blue to say those are the ones I'm actually counting, which is these. And there would be 21. Because in that case, we would have to count 2, 1 is the same as 1, 2, right? Because what would the dice roll be? 3. And if I don't know which one is dice 1 and which one is dice 2, there's only 21 possibilities. So in reality, we have to ask ourselves whether events are distinguishable or indistinguishable, because it's going to change the way we count.
Professor Peterson?
Yes, ma'am.
So
When working with sets, we have two, well, there's more, but these are the first two set operations we want to talk about. So the intersection of two sets, A and B, written with this upside down looking U thing, is the intersection of the set A and B. Is the set of elements common to both set A and set B? That is, A intersect B is the set of all x's such that x is in A and x is in B. So this symbol is equivalent to the logical AND. Two sets, C and D, are called disjoint if C and D have no elements in common. That is, C and D are disjoint means that C intersect D is equal to the empty set. That means that C and D share no common elements. The other operation we want to talk about is a union. So the union of sets A and B, written A union B, and this is our logical OR, is the set of all elements that are in set A or in set B. That is, we don't need that. That is, that are in A or B. So the complement of a set, or the set A, written A prime or A bar. Our book uses the prime notation. A lot of books use the bar notation, so be familiar with both. Is the set of all elements that are in the universe, but not in A. So A prime is the set of all x's that they're in the universe of all possible items that can belong to a set, but the ones that are specifically not in the set A. All right, so let's do some examples illustrating these ideas. So let's let our universe, or the set of all possible elements, be P, Q, R, S, T, U, V, W, X, and Y. Then A is the set P, Q, R, B is the set Q, R, S, T, U, and C is the set R, U, W, and Y. We want to find the following sets. So for A, we want A union with C. Well, our set A is P, Q, R, and our union is the OR C. And that is R, U, W, and Y. So the set A union C is the set of things that is in either set. It's either in here or in here. When simplifying a set, remember, we list each element only one time. So there's a P in our first set and no P's in our second set, so we add a P. There's a Q in our first set, no Q's in our second set, so we add a Q. There's an R in our first set and an R in our second set, so we only add one R. Then, since it's an OR, we've done everything in our first set. The rest of them just come along for the ride. So our set A union C is P, Q, R, U, W, and Y. So essentially, it's everything that was in A or everything that was in C. But with sets, we never repeat elements, and the order that we write them in doesn't matter. So if I would have written Y, W, U, R, Q, P, that would also be a correct answer, because the order we write things in doesn't matter. All right. So now let's take a look at A intersect C. So this is the stuff that's in A and B. So we have P, Q, R, and R, U, W, and Y. Well, this time, the AND tells us that it has to be in both A and B. What is the only element that is in both A and B? R. So the intersection, or the AND, is only R. All right, so let's try our next one. C is A union B. So our A is still P, Q, R, and our B is Q, R, S, T, and U. So our union is going to be P, Q, R. This doesn't have any P's. Q and R are already taken care of, so then it's going to be S, T, and U. D wants our intersection. So what do these two sets, A and B, have in common? Well, this time, the two sets have Q and R, so the intersection of A and B is going to be the set Q, R. All right, let's take a look at E. E says find B prime. So B prime is the set of all things that are in the universe that are not in B. So we want the things that are not in Q, R, S, T, and U. So our universe was equal to P, Q, R, S, T, U, V, W, X, Y. So P, Q, R, S, T, U, V, W, X, and Y. That's our universe, right? But now we want the things in our universe that are not in B. So we take everything that's in B and we take it out. So Q, R, S, T, and U. So then finally, B complement is what is left. So it's P, V, W, X, and Y. So the complement of B is the set of all things in the universe that are not in the set B. All right, the next one is for you guys. I want you to find C prime. All right, so our universe is still P, Q, R, S, T, U, V, W, X, and Y. And C is R, U, W, and Y. So if we take the elements of C and remove them from the universe, we get rid of R, we get rid of U, we get rid of W, and we get rid of Y. That gives us our C prime is the set P, Q, S, T, V, and X. So that would be the complement of C in our universe. The next thing we want is A union C prime. So our set A is equal to PQR. And we just calculated C prime, so it's going to be the OR of each of these. So A union C prime is going to be PQR, because that's the stuff in A. We've already got P, we've already got Q. This one doesn't have an R, but then we have the rest of this because it's an OR, so S, T, V, and X. And we have one more, which is A intersect C prime. So A intersect C prime is going to be our P, Q, R intersect with C prime, which was our answer from up here. So P, Q, S, T, V, X. The only things these have in common are P and Q. So the intersection of A and C prime is going to be PQ. So that's our and our or, so our intersection and our union of sets and complements. So we did all of these set operations by hand. We want to talk about the idea of what is called a Venn diagram. So Venn diagrams are a visual way to represent sets. So in a Venn diagram, the universe is represented by a rectangle, and sets are represented by circles. I'm going to call that set A, and we're going to call this set B. So if we have set A, and I'm going to color code it as yellow. If I have set B and I color code it as blue, in our picture we'll notice something right here in the middle. Well, where the two sets overlap, what color do I get? Green. This green portion in our picture is the intersection, or the and of our two sets. So that represents A intersect with B in terms of a picture. So in our Venn diagrams, we can draw and label things to talk about sets in terms of pictures. There's no reason I could not add another loop to this. So if I added another circle, I would now have 3 sets plus the universe represented in this Venn diagram. So let's go ahead and use our next example to draw a Venn diagram. So first things first, this is exactly the same example we just did, and we're going to be able to confirm all of our computations by drawing a nice picture. So same set U for our universe, same sets A, B, and C. And we want to locate all of the elements in a 3-loop Venn diagram. So let's draw our universe. That's a lot of letters. I'm going to need more space. All right. So we know our universe is P, Q, R, S, T, U, V, W, X, and Y. The set A we know contains, so let's label these. We have A, B, and C. We know A contains P, Q, and R. But when we look at our set, we have R here. R also belongs to B, and R also belongs to C. So where would I have to put R in my diagram? Because it has to be in both A, B, and C. Yeah, it's going to be in the very middle here where all 3 of them overlap, right? So then I look at my next letter in A, which is Q. It is also in the set B, but it is not in the set C, right? So I need A and B. A and B is going to be up here. So that's my Q. And then I go to my next one, which is going to be P. P is not in B, and P is not in C. So then P is over here in A. All right, to help me keep track of this, I'm going to cross off in here after I have placed each of the elements. So we know where P, Q, and R are. So now we go to our next set, which is S, or into our set B, and its next element is S. So we know S isn't in A because we've already done with A. And is S in C? No. So S is only going to be in the set B, so it goes over here. So it's done. T is not in the set C as well, so it's going to go over here. And then we have U. U is in the set C. So B and C is going to be down here, and we're going to get U. So now, we have the 2 things that are left in the set C, which are W and Y. So hold on, let's see. I placed S, I placed T, and I placed U. And in my next set, we're now to see I have W and Y, and they're not in any of the other 2 sets, so they're done. They go here, W and Y. Well, what 2 elements have I not placed? The V and the X. So they're in my universe, but they are not in any of the sets A, B, and C, right? So they're all out here. So then what would be our set A and B? Well, that would be this football shape right here, right? So A and B would be the set QR. Well, that was our answer to D up here, right? Oh, Q and R, right? Because in our Venn diagram, That is this portion right here. So that's A and B. So what would be A and C? That would be this part right here. So what's the only thing that's in A and C? R.
It doesn't matter that it's in B.
We didn't ask about B, right? If we just asked if it's in A and C, the fact that it's in B is not important, right? So now, what if I asked you for the things that were not in A and or in B or in C? So what's the complement of A union B union C? Yeah, the X. So it would be the things that weren't inside any of the circles, right? So these Venn diagrams give us a visual way to think about sets. So you can go through and create Venn diagrams like this. You can do your stuff this way like we were doing up here. Both of them have advantages, right? I like Venn diagrams, and a lot of people do, because it visually lets you see where everything is. And human beings tend to be visual creatures. It works out really well. All right, the next thing we need to talk about is the Cartesian product. So, where have we heard the word Cartesian before? Well, that's our fancy $4 word for the XY coordinate plane, right? Is the Cartesian coordinate system. It's the set of all ordered pairs x, y. Well, that is a special case of the general Cartesian product. So the Cartesian product of two sets, A and B, is the set of all ordered pairs, A comma B, where A is from the set A and B is from the set B. So in set builder notation, A cross B is the set of ordered pairs where A is from A and B is in B. So for example, if the set A contains the elements A, B, C, and the set B contains the element red, then A cross B is the set of all possible ordered pairs where the first coordinate comes from A and the second coordinate comes from B. So the ordered pairs would be A pairs with red, B pairs with red, and C pairs with red. Because the set B had only one element in it, right? Red. Okay, example 11. What if my set A stays the same, but now I have my set B is the set red, blue. Then A cross B would be the set of all ordered pairs. Well, I would still have A red, B red, C red, but now I have a second coordinate in my set B. So it would be A blue, B blue, and C blue. So I'm pairing every element of my first set with every element of my second set. So if I do this, I am pairing every element of this set, A, B, C, with every element of the other set. Similarly, if I do this, I'm going to pair every element from my first set, A, B, C, but now they have to pair with the second coordinate of the other set. So it's the set of all possible ordered pairs where the first coordinate comes from the first set and the second coordinate comes from the second set. And you would have to do that for everything in the space. Well, if you think about the Cartesian coordinate system, x and y, the first coordinate is all possible x's. The second coordinate is all possible y's. And the ordered pairs represent the Cartesian product of the x-axis crossed with the y-axis. There's nothing special about the set of real numbers. This can be done with any sets. So the first set, A, just tells us the possible values of the first coordinate. The second set tells us all the possible values of the second coordinate, and then you pair them up. So one way that might help you visualize this is something similar to what we did in the beginning. If I do A, B, and C, and then I do red and blue, what are my possible pairings? Well, A red, B red, C red. Then it would be A blue, B blue, and C blue, right? So we're just listing all possible ordered pairs, which looks an awful lot like if you did 1, 2, 3, 1, 2, 3. What's this point? 1, 1, 1, 2, 1, 3, 2, 1, 2, 2, 2, 3, 3, 1, 3, 2, 3, 3, right? We're doing the same thing, but instead of just arbitrarily using numbers, we can use arbitrary sets. So the Cartesian product just says pair up everything in the first set with everything in the second set. It may be helpful to make a rectangular diagram if you're having a hard time visualizing what belongs in a particular set. All right.